Hello, everybody. I'm Gordon Stove. I am the CEO and co-founder of Adrok. We're a technology company based in Scotland, and we have developed a radar technology for searching deep into the ground for mineralization. So I'm here at the European Mining Convention to introduce the technology and talk about some case studies. So with this particular presentation, we'll be talking about sulfide targeting. So looking for various sulfides, lead, zinc, etc., deep into the ground. So through the collaboration of our mineral exploration companies, we had a challenge set by them, which was how do we see deeper into the ground? So the economic demand and supply situation just now in the mining industry is that there's a huge demand for sulfides, in particular copper for the electronics industry, and the supply is not quite meeting the demand just now. So if you look at this graph here, I mean, looking through time, I mean, the mineralization discoveries have been coming deeper and deeper. This is depth in meters down here. So the discoveries have been deeper and deeper under the ground, and it's becoming a lot more challenging to find these sulfides. So at Adrok, from the demand from our tier one clients, we developed our hardware, our software processing, and our interpretation techniques using neural networks and artificial intelligence, and also clever statistics to help better find sulfides in the ground. So the technology itself that we've developed is called atomic dielectric resonance. We have a transmitter and a receiver. We send and receive radio waves into the ground. So we send radio waves at a broad band of frequencies from 1 megahertz to 70 megahertz, all at the same time. And we send that continuously pulsing into the ground and catching the returns. So we pulse the depths, the signals into the ground. For the mining industry, it tends to be from ground level down to 1,000 meters deep below the ground for mineralization. So we have a receive control unit that catches the returns and then digitizes the analog signals. And we then present that on our software, and we can process the data that comes back. The signals are set up through the transmit control units here for signal generation. And we get a reflection and a refraction back from different changes in rock types in the ground. Now, the rock property that we measure is the dielectrics of the material. We also measure the conductivity as well. So dielectrics and conductivity are very closely related. So whenever there's a distinct change in dielectric, we get a reflection back from that layer, or that boundary layer. And we send the radio waves into the ground in the time domain and also the frequency domain, but it's the time domain that we're interested in for depthing, because we can convert the time into depth using triangulation techniques, using wide angle refraction and refraction techniques, or normal move out techniques. So we're in some cases similar to ground penetrating radar in the sense that we use radio waves. Although we use multiple frequencies at the same time, not just one single frequency into the ground. And we use a lower power source than the ground penetrating radar. But ground penetrating radar tends to use megawatts of power. We use milliwatts of power. And we're similar to seismic in the sense that we are a reflection technique. I mean, sound waves are sinusoidal waves. So there's energy, which is the amplitude of the wave. There's the frequency of the wave, the amount of times the wave passes through a certain point. And there's also the phase relationship, the orientation of the wave as well. So energy, phase, and frequency are what we measure, and we analyze that with our radio waves, which is very similar to the seismic acoustic waves that they analyze. So in the field, the system specification is here. I won't read it line by line. You can take a screenshot of it if you want. But the thing to note is that the equipment is very portable. It's very small, very portable. It fits into these boxes, cargo boxes, which then fit into the back of a Jeep or an SUV very very comfortably. And we can fly the equipment through commercial air jets using excess baggage around the world, which is very, very quick and easy. So the other thing to note is the power. So we do use little power and we transmit little power. So it's milliwatts of power that we send into the ground. And we are battery powered. So we use rechargeable lithium batteries, which are around about 12 volts in battery power. So one of the projects we started with, we're as a company, we're 20 years old, but we spent the first 10 years of our life doing research and development. And then we entered into the commercial world as a service company. So when we started doing commercial projects, we met a company in Canada called Teck, which is Canada's largest natural resources company. And we did a test underground under a mine. So they had a care and maintenance mine called Ponderay in Washington State in America. And we went under the ground. If you can see my cursor, we went into the ground here, the transmitter pointing up and the receiver also pointing up, but catching the returns back. So transmitter receiver pointing vertically up through the mine, going through solid rock. In this case, it was limestone, all the way up 355 meters to a water body, which is a river at the top, and then into air. So a nice little test, 355 meters worth of rock, and then 8 meters worth of water, and then out into air. So the dielectrics for all these properties are very different. So rock is between 5 and 15 for limestone, depending on how dry or wet it is. And water is 80 and air is 1. So air and water are opposite ends of the spectrum for dielectric values. So here, going up through the rock layers with the dielectrics for the rock is very constant, very sort of bland, nothing unusual. It's a very homogeneous limestone block at Ponderay. And then we're into the water. So the water is a big spike at 80 in terms of dielectric, which is a fantastic fingerprint and standout response for us, which is great. And that was just the dielectrics. And even for the energy reflections, so what was being absorbed and what was being reflected, we had a good change in different materials and different layers. So we've got within the mine, we've got air in the mine, and then into the rock, and then out into the water as well. So we published this at the Society of Exploration Geophysicists, SEG, in 2014 in Denver, and the paper can be downloaded online, or it could be downloaded from our website. So Teck, on the back of this work and also some other field work we did around the world, invested in the company. So they're a shareholder in the company, and they have been providing us some services since 2011 when they came and joined us on board. So from the same project, this is the video of the signal. So we've got the dielectrics down here with that great spike up here. This is horizontal. It's not quite, we've had to move it just for the sake of a PowerPoint presentation. But if you can imagine, this is inside the mine here, going vertically up into the ground level, which is at the right-hand side of the screen here. So if I press play, oops. Yeah. So the signal at the top, the red signal here, traveling through the ground, nice standing wave. That's what we tend to send into the ground. A nice standing wave keeps its shape, keeps its amplitude through the rock, through distance. And then, whoa, we get a big response, big reflection back here, this big target here from the water body, which is giving us a big signal response. So that whole experiment was a fantastic result. As I say, went through 355 meters of rock and then water and then out into air. We also did transillumination tests, which is pointing the transmitter and receiver towards each other through the rock body to show that we were getting true signal penetration through the rocks as well, which is great. So in terms of sulfide methods, one of our clients in Australia, City Gold, they have a gold project in Charters Towers in Queensland. They use all sorts of geophysics to try and map their gold reefs and their orogenic reefs in the granites. One company they did use was, one technique they used was a ground penetrating radar by a company called Mala Geophysics. And they went out to do some surveys with this kit, and they got some images back which were quite shallow. It went down sort of 10 meters, and then maybe 15 meters, and then beyond that, the signal wasn't getting very strong. It was very noisy, so they weren't making much sense of the images. So yeah, so the traditional ground penetrating radar, conventional ground penetrating radar, is good at imaging the bodies to a certain depth, but it's very shallow. It's very near surface. But I mean, if your targets are near surface, then it's a reasonable technique. I mean, it does through the dielectrics and differentiate different materials. So you can differentiate sulfides using a ground penetrating radar for shallow targets, which is good. But in the City Gold project, their targets were a lot deeper, so they had to use a deeper radar technique after seeing the shallow technique working. So they found us, and they asked us to come out and to Australia and do our surveys. There is another radar technique which we found, which was published by Hammond and Spreck in 1991, and they produced a radar technique. They developed their own radar antennas, and they went down 200 meters through an ice body, through subglacial materials, and again they managed to see disseminated sulfide zones through the material, which is great. So I mean, our technique, I mean, we borrow from this experience, the radar experience from ground penetrating radar, but we can go a lot deeper. So the energy reflections that we get are a lot deeper through the subsurface, which is a huge advantage, and that's why at Charters Towers with our client City Gold, we had such a successful result deep in the ground with that. So the reflections that we got back from City Gold were the energy logs. So this is the E log that we call. So the spikes here that we're getting, the energy spikes, were coincident, corresponding to the sulfide percentages they found from the core samples that they drilled, and the acids. So the presence of sulfides was given a reflection on our energy signals, which is really good. So in terms of disseminated sulfides, so we can see the reef sulfides there. In terms of disseminated sulfides, our clients were wanting to know, can we find a unique fingerprint using our technique for the sulfides versus the country rock? Can we help constrain the target area and target depth prior to drilling? Can we provide a sulfide probability map to better inform drilling planning? And can we help develop a technique that will enable mineral explorers to drill undercover, deep undercover, with much greater confidence? So these are the main challenges for our disseminated sulfide targeting innovations, which we've been developing over the past 5 years. So in terms of the energy and frequency, if you remember this sinusoidal wave of the radio waves coming back, so we get the energy, the amplitude, the strength of the signal, and the frequency, the sort of pulsing that comes back. So we see from the sulfide pyrite information that there's a big sulfide body here between 600 and 700 meters below the ground, and we can pick out, there is some spikes around here, but you really need to zoom in on the information. I mean, a lot of it does look like noise for first glance, but if you're patient enough and you've got enough meticulous correlation statistics analysis, you can start picking out data quite quickly and information from the data. So we can assign numbers which are correspondent to pyrite zones, and we can start labeling and fingerprinting the sulfide signatures and the fingerprints based on our signals, the energy and the frequency responses. And we can do a depth discrepancy as well. I mean, our depths are not always 100% accurate. I mean, there are plus or minus 20 to plus or minus 5 meters out is the typical range for our measurements. But again, this is over 1,000 meters through the ground, and we're collecting data from the surface. So this is a huge distance that we're sending our information through and our data through the ground. And we're not drilling the ground yet. I mean, we're saving money by not drilling. So yes, I mean, in terms of our results, I mean, we've got our 8 components and 3 components analysis, and both give good information about the sulfides. 3 components is a bit more simpler. It breaks it down into sort of chunkier sections. And you can start making a cutoff analysis of what's exactly the pyrite's unique pyrite signature. So for here it was 20 was the cutoff, 12, for example, here it was a cutoff, giving us the unique big sulfide body down at 600, 700 meters through the ground. So we've got lots of case studies using this applied WSCC technique, which we developed. I mean, the COVID pandemic has actually helped us concentrate our efforts on honing in and practicing our skills on the WSCC. So we've been doing that a lot. We've been going over old historical legacy projects and really refining our results and picking out the results, which is great. This is a lead zinc project which we did in Ireland. So our virtual boreholes here going down got good hits, which of course coincided with the inferred mineralization zone from the client's geologist, the chief geologist, giving the interpretation there. And of course, they've got their own drill results as well, which they can build this information from. So our hits were very, very spot on. I mean, this is, again, we collected data down to 1,000 meters. The client drilled down to, well, the deepest they drilled down to is 700 meters. We think we've got these big bodies down here, which are slightly deeper, which haven't been drilled, but haven't been verified. But the shallow ones here have definitely been drilled and definitely been verified. So the client was very happy with that. Further zinc projects. So yes, I mean, the sphalerites, the pyrites, lithology can all be matched up to our results here ahead of our predictions are ahead of drilling more zinc projects. So yeah, I mean, there's another good one. This was the Irish project again. So yeah, so we're going through, in this example, we're going through Walsrosian limestone into the sulfide zone, the lead zinc sulfide zone, and then into the lower arbolaceous, and then into the basement. So we can clearly see the mineralization here. We can see some Walsrosian limestone up here. We see a change here, and then we're into the change down at the basement again. So we've got all these different changes of the different lithologies through the subsurface. And again, we haven't drilled this. This is all from the surface, going down 1,000 meters through the ground. There's another look at a different angle. So the end results, we can give the client, we can give them these virtual logs through the ground with the geology in the background, or we can give them just X marks the spot. These are the depths at which they should be drilling to hit their targets. It's entirely up to the client how they use the data. So yeah, so I mean, these case studies show good correlation with both the 8 and 3 component WSCC and for the sulfides, for sphalerite, galena, and pyrite. We can differentiate between the mineralization and the host rocks, the different host rocks. It's very clear. And yeah, we're very confident in these results. So we can build up models for these results. This is a project in Australia. This is at the Bracunga site in Australia near Adelaide. And we did a profile scan, a two-dimensional cross-section through the subsurface here. It's a big rectangular section here. And also our virtual boreholes. So our virtual boreholes are the vertical lines here. The clients drilled these angled lines. But we can clearly see the mineralization, and also through the 3D the model for using our 2D slice, we can see the structure of this dipping sulfide bearing grey wacky units, which they mined out. So in summary, this presentation, we've demonstrated that our radio wave technique can go deep into the ground. It goes for mining applications, it goes down to 1,000 meters through the ground using 1 to 70 megahertz frequencies. We can see sulfides. We've developed this weighted sulfide correlation criteria, WSCC, which is showing great results with comparing with the ground truth of the drilling sites and also with our predictions ahead of drilling and then verified by drilling. So Adrok is very confident that it represents a major step forward in the use of deep penetrating radar for the identification of sulfide techniques, sulfide targets without the need of drilling. Therefore, we can reduce the time, the cost, and also the environmental impact. There's no drilling, it's non-destructive, non-ionizing of the ground, and they can go deep undercover for undercover exploration. We've got lots of case studies on our website if you want to visit our website, or you can email me. My email address is here. You can ask further questions about your technology and really grill me and ask me some challenging questions about what we do. Just as a bit of fun during this COVID times, so we think we've smashed through this COVID period by developing the sulfide targeting tool and perfecting it over this COVID lockdown period. And we think we'll be leaving other companies standing still while we'll be running and celebrating with the winning goal. So thank you very much for watching, and please be in contact if you want any further information. Thank you.